Okay, so throughout this morning, listening to the discussion, I took my title and removed hydrous, um, kind of reconsidering what I wanted to talk about today. And then through Kanani's talk, I pretty much just rewrote my entire talk in my head. So I'm going to kind of just respond largely to the questions that have already been posed. And in a lot of ways, the focus of my work over the last several years has been looking at, or partial focus, has been looking at really where is water as a very important volatile component of the Earth's interior with dramatic effects on everything from wave speeds to melting temperatures to the evolution of the planet through time. And so we can look at, for instance, a lot of these different, on the left, we've got the mineralogy. We've seen that on the right, coming out of University of Minnesota. For instance, discussions of what the total water storage capacity is in the mantle. And that's great if I've got this big sponge that can soak up a bunch of water. But to some extent, we also want to know how much water is actually there. And so a lot of my work has been really focused on trying to discern what signals we could find in the Earth, what sort of geophysical signals would tell us whether or not the sponge of, for instance, in what we have here of the transition zone, if that sponge is sopping wet or if it's been squeezed dry. So I want to know what the physical properties of water-bearing and dry minerals would be under realistic conditions. So I'm going to start off by responding to Vijay's question, which is, do I like experiments or theory better? And really what I'm interested in is this scientific question. And I have a couple of tools. One of my tools is a Diamond Danville cell. One of my tools is first principles calculations. So I'm going to, this is kind of my general approach, this combined approach of synthesis and measurement of samples of things that are constructed under, for instance, realistic pressure and temperature conditions. This is compressed, so I picked an SLS instead of another synchrotron to illustrate collecting data off of these things. And from the data that I get, I can construct really an atomic scale view of what some of these minerals look like, how these minerals are actually put together atom by atom. And I can test a lot of those ideas then by going instead of, in the experiment, I can fix composition, pressure, and temperature. In the computer, I can actually fix where those atoms are in space and then calculate the energetics of those systems. I use the Ohio Supercomputer Center, which in some ways is analogous to the Minnesota Supercomputer Center. In other ways, it's very distinct. And then from that, be able to calculate everything from charge densities and energetics. So just the Ohio Supercomputer Center, I'm not a representative of the OSC in any way. This is pulled off of their website in the last 24 hours. It was established in 1987 by the Ohio Board of Regents. And Ohio is this incredibly democratic state, and that's not in a politics. That's a everyone has equal access type state. And so the OSC is not for the Ohio State University, the Ohio State University. It is for the state of Ohio, and that's all the universities and private industry all working in Ohio. And I think that actually kind of sets some of the mentality of what it's like to work with them. Power. They provide computational something, power and data storage to scientists and engineers and private industry in the state of Ohio. And it is on a proposal basis. So I copy and paste words out of proposals I've already written and into a document. I send it to them, and I can be awarded what converts to be about 500,000 processor hours per proposal. You can write larger proposals that get a more careful review, but I get 500,000 hours pretty much just for showing up. And this is something that for my own purposes is more than sufficient. I'm on my second proposal since starting my tenure track job. And the only reason I had to go on to the second proposal is I had a grad student who wrote a runaway script that didn't get noticed right away. And so the OSC provides both open source and proprietary codes, some of which are by contract basis. And they also provide assistance in compiling other codes. They have directly assisted me in compiling both VASP and Quantum Espresso. Some of the codes that are there are not, they have codes that are really of interest to a variety of different fields. Things that are, ab initio type codes that are really only used by the biologists, and then they also have more chemistry and solid-state physics type codes that are available. Neither VASP nor Quantum Espresso are just regularly available to everyone. And a couple other things I had to sign contracts to get access to. But VASP, for which I hold a license, in Quantum Espresso, which of course is open source, they have really assisted me as someone who understands how a computer works, and I understand what compiling is. But if make doesn't work, I'm kind of without hope. And they actually provide that service, and it's in fact quite easy to get everything done quite quickly. Something else that came up that people were talking about queues and whatnot. I'm aware of what queues are, but it turns out that it looks like I've never actually had a job held up in a queue. So there's also, I'm ignorant of some of these things, right? I am an end user. And, but I don't have problems with competition for node space. And so it has not been an issue for me. And so the OSC provides everything really that I need. They also run users meetings. They run tutorials on everything from MPI programming to how to use MATLAB, and provide seminars to really to help, primarily focused on graduate students, to really help educate the users of the OSC. So I'm going to give one example of the type of work that I've done, where I've taken kind of a question that kind of nucleated from an experiment that I did, looking again at this question of, is there water in the mantle? And how much we know that ringwoodite we can measure, we can synthesize ringwoodite that holds more than 2% water. We know it can hold water. The question really is does it hold water? And looking at the, this is quite dark as well, looking at the structure of ringwoodite with the spinel structure, the first, as an experimentalist, what you do is you take all the components together, you put them in some sort of rig up to the right pressures and temperatures, and you hope it synthesizes the right phase, and then you measure something about, for instance, how much water got incorporated. From the ab initio calculations, you start with either some sort of one of Arnhem's types of one of Arnhem's sorts of approaches to looking at how these might be arranged. But with these defects that we're addressing, it's an incredibly complicated method. And so the approach that I've largely taken is very logical guesses. We have, for instance, spectroscopy, where we can look at, we have a fairly solid sense of how hydrogen enters the structure of the spinel structured Mg2SiO4. But there's some things that are quite complicated about it. We can use our intuition based on what we understand quite a bit more thoroughly based on things like olivine and wadslite, but ringwoodite seems to violate that to some extent. So we can start by using our intuition on how hydrogen is incorporated in there. And in looking at the structure and contemplating the structure, what it was occurring to me is, in fact, spinels are notorious for cation exchange between the two sites. So you can have, for instance, for the Mg2SiO4, a swapping between the magnesium and the silicon site. And this disordering has been suggested. It's been observed directly in a lot of other spinels, and it's been suggested in these spinels, but it's very difficult to measure. Turns out, if you look at, for instance, the X-ray, the interactions with X-rays, when looking at X-ray diffraction, it's very difficult to discern whether or not you've got a magnesium or a silicon atom in the same site. And so this turns out to be something that this is a way to torque the local charge balance and therefore can influence how hydrogen is incorporated into the sample. So I ended up distracted for a year as I started looking at the cation disorder without the hydrogen. I'm not even going to address the hydrogen today because we don't have time. And I just looked at the disordering between the cation sites. And as really the starting point so that I could start this series of calculations to address the hydrogen incorporation in these samples. So we know this is something that happens quite frequently with other spinels. We suspect this happens with ringwoodite, but the experimental evidence is tended to be of secondary nature. So I did a series of calculations. I calculated the relative energetics of the fully ordered versus the partially disordered structures. And this is following on, I want to make sure that it's clear, this is following on the previous calculations that have been done by other people in this room. But looking at now with the increasing capabilities of processors and whatnot, being able to look at this at very minor amounts of disordering. And calculated, for instance, the elastic constants as an effect of either partially disordering and comparing it to the fully disordered structures that have been previously published, for instance, by Boris. And then, wow, normally this only happens as a Mac to PC problem, not Mac to like modern Mac. And so then I actually, we can take into account some of the thermal effects. We can do large molecular dynamic calculations, but sometimes you're using a really big hammer to push in a little tiny pin. And so there's oftentimes quite a bit of insight that can be drawn just by looking at the thermodynamics, making the approximation. I'm going to assume ideal configurational entropy. And you can put in some various tests to calculate the relative energetics, see whether or not this is a decent assumption or not. And generally, and particularly with spinels, it's been shown for quite a bit of time that using, for instance, an ideal configurational entropy is a good approximation. And then from that, you can calculate that the degree of disorder should be temperature dependent. Now, this isn't anything that's all that new for the people that have really been looking at spinels. But pointing this out and plotting it for ringwoodite, it dawned on me we had something additional that was happening here. And so the calculations that I did found, in fact, an increasing amount of disorder happens with higher temperatures. It's not a big surprise. But also predicting that the amount of disorder that you find below 1,000 or 1,100 Kelvin is quite low. And so when you go from extrapolating measurements, for instance, how elastic constants vary as a function of temperature, we want to be able to extrapolate things up to the conditions of the Earth's mantle. We need to know how elastic constants vary as a function of both pressure and temperature. But if you're looking at this with an effect of temperature, but you stop your experiments at 1,000 Kelvin, And this is done oftentimes for very practical reasons. You get up to 1,000 Kelvin under ambient pressures, your ringwoodite sample starts to fall